7.4 is the characteristics of logarithmic functions with base 10 and base e. So what we're going to look at is the log functions. We've done quadratic and linear and cubic, and now we're going to check out an exponential. We're going to check out log ones. Logs are basically the opposite of an exponent. So we're going to compare what these graphs look like when you're working with a log function as compared to what we looked at when we were doing exponential functions. So logarithmic functions are a function of the form y is equal to a log bx, so that's our general form, where b is greater than 0, so our base, and b cannot be equal to 1, and a is not equal to 0, because of course if you multiplied anything by 0, your answer is just going to be 0. And a and b are real numbers. So the expression log base 10 of x is known as the common log, or a logarithmic with a base of 10. The expression is often written without the 10, so it's kind of like our standard 1. So when you don't have an exponent, or when you have a log that's written and there is no subscript number, then you assume that it's a 10. So it says, so the two functions y is equal to log base 10 of x and y is equal to log of x are the same thing. Another tip, the function y is equal to log base 10 of x is equivalent to x is equal to 10 to the power of y. So as I said at the beginning, log and exponential functions are just inverses of each other. So when I'm looking at x is equal to 10 to the power of y, what we're looking at when we're doing log functions is what is the exponent that has to be applied to the base to get you whatever value that you're looking for, in this case value of x. So if I take a look, y is equal to log, base 10 of x. To rewrite that, 10 is my base, so that's the base of my exponent. I want to find out what is the exponent that I have to apply to that base so I get the answer of x. I'm not sure if my screen is flashing for you or if it's just doing it for me, but it's a little annoying. So it says, for example, log base 10 of 100 is equal to 2. If I switch this into an exponential function here, it would be 10 to the power of what, so our y, is equal to 100. So that's where we get the answer to. A log with a base of e is called the natural logarithm, and it is written as ln x. So whenever you see ln x, that means we're looking at natural log. The function y is equal to log base e of x, and y is equal to ln x, or natural log x, and x is equal to ey are equivalent. So y is equal to log e of x is the same thing as writing log or ln x, just like in this example here, writing with the base 10 or without the base of 10 is equivalent. Changing that into a exponent, I have my base is e. I'm trying to find what power, so the y, will give me my answer x. Oops, sorry, that shouldn't be an A, that should be a B. So my exponent, I don't know why that happened. Written exponentially, I have by is equal to x. Written as a log, this is log b of x equals y. So that's where they just change spots to go from log to exponent. Okay, so we're going to use the graphing calculator to see what happens when I have just a basic log base 10 or when I switch my a values from 2 to 5, and we're going to fill in the table. So I'm going to do the first one with you, and then the other ones I will punch them on there so that you can see what the graphs look like, but I'll just fill in the table without doing those steps, just to save time. So you go into your calculator, and I want to substitute in y is equal to log base 10 of x. So y equals, I'm just going to clear that. I go into math. And in math, the 0, if you move all the way down, oh, no, sorry. This one's, that's for another one. It's the a. It's even lower than that. Go back to math. Go up. The a is the log base function. So I hit that. So log base, my base is 10. And I'm finding base 10 of x. So that's what I'm looking for. I can then graph it. I might have to change my window here. I'm not sure. Well, that's pretty close. What is my window at? Negative 10. 10 going up by 1. Okay. Gives you a good enough idea. So now, if I want to fill in my table here to find out what is my values, there's a couple of ways of doing this. One way that I showed you in the other section was to do that, calculate the value one. So if I do second calc value, x is equal to -1. So if I try that, it doesn't give me a solution. So that means there is no solution for it. If I were to try second calculate value of, let's try 3. If x is equal to 3, it tells me it's 0.477. So that's one way of doing it, is to go through and punch in whatever values you're looking for x that are in the table. And if it was just asking you 1 or 2, this is a good way to do it. But if you're doing a list of them like this, it's going to take you a while longer. So go into the table function. Go second, and then the graph. That gives you table. And this gives you the values in there. And you can move up and down. If you want to change, so that if you're going up by 10s instead of going up by 1s, if you hit the plus sign and then tell it, okay, give me the numbers going up by 10s or by 2s or whatever, you can set that as. So I can see -1 is an error, 0 is an error. When I get to 1, it's 0. 0.301. 0.477, 0.602, 0.699, 0.778, 0.845, and 1. Now if you wanted to check these to see if they're right, so if I did y is equal to log base 10 of, let's try 1, because that one, what this question is saying, if I do this exponentially, 10 to the power of what equals 1? What has to be a 0? So the other one that gave us a whole number was 10. So if I try y is equal to log base 10 of 10 and turn that into exponential, I have 10 to the power of what equals 10? Well, it's a 1. So there's my answer. Okay? So now what you would do for these other ones, I'll just slide this over. Y is equal to, and you, well, I'm going to see what happens. I'm going to put this other one in here. So I do my math. I want to go up to log base. So it's log base 10, but I need a value in front of there. I should have put that in there. So I'm going to insert, because I forgot to do that first. 2. So I should have done 2 math and then that log. So 2 times log base of 10 of x. I just want to see what happens when I graph it. It's going to be okay. So if I hit graph, that's what it looks like. So it's stretching it a little bit, stretching it on the y. I'm not sure what's going to happen with my table though, so let's see. It should give me, there we go. Excuse me. So on my table there, I can see what's happened to my values. So I had error and error. And then once I got to 1, it was 0.602. and then it was 0.954, 1.204, 1.39, so that's going to round to 1.40, 1.56, 1.69, 1.81, and 1 decimal, whoops, oh, 6, 7, and then 10 if I move down. Oh, that has to catch up. So 10 was at 2. So if I compare the two, I can see by putting that 2 in front, my A value is equal to 2. It doubled all of my solutions. So 4.77 doubled is 0.95. 0.301 doubled is 0.602. 1 doubled is 2. So then, by logic, then, if I multiply by a 5, so I'm doing 5 math, move up to, oh, I must have a bad connection somewhere. Log base 10 of x, graph it, where did it go? Oh, because I put a log base of 1. Okay, now let's graph it. So it's my black graph. You can see it's stretched it even further. If I do the table, I'm not going to move up, but this one will do an error, this one will do an error, this one will still be 0. And then if you take a look at the numbers, 0.3 for x value of 2 turned into 1.5. So it did multiply it by 5. So 1.50, I'm just going to do it to 1 decimal place. 1.5, 2.4, 3.0, 3.5, 4.2. Oh, did I miss one? That should be 3.9 and then 4.2. And then 10 ended up being 5. So that's just logical that it ended up that way. I just have to cough. Okay, so the next page then, and I'm going to do a split screen on here so that we can compare these graphs, but no, it won't let me move it. Okay, anyway. Oh, this is going to be annoying. Okay, so next page asks that we graph it. So I'm just going to zoom in here. So I have both pages on. Because then it says to sketch the graphs. So based on the information, if I went further into the negative values, and I'll bring up calculator, hopefully it'll cooperate with me. Oops, we have errors. So, oh, okay, I'm going to pause and see if I can fix. Okay, I'm not sure if I actually fixed anything or not, but when we go to draw these, we have our values here. So we had errors at 0, errors at -1, and errors continuing. If you go in your table, there'll be errors all the way up when you have the negative values. Once you got to 1, your value was 0. So you can use, and if you look in the graph, you can see we go into the negatives in the y. We never go into the negatives in the x, but our y values can be negative. So if you wanted to try any value, so let's do a value of, say, x is equal to decimal 0.00001. My y is equal to -5. So you can put in any number you want. It can be as small as you want, as long as it is not going to be a negative value. Okay? 0 will get you 0, or sorry, 1 will get you 0, 0 will get you error, but anything just a smidge over 0 is going to give you a value. So that is why our graph, and even though it doesn't show it going all the way, this graph would continue down forever. It just would never cross that y-axis. So when we go to draw these graphs for y is equal to log base 10 of x, at 1 we had x equals 1, we were at 0, and at x equals 10 we were at 1. I'm just going to zoom back to the regular screen so that you can see this a little bit better. Where's my zoom? There we go. Okay. Oh, I didn't even have that in the right spot. For y is equal to 2 log base 10 of x, at 1 we were at 0 when x was equal to 10, y was at 2. Was that it? No, 2's here. Okay. And then for the y is equal to 5 times log base 10 of x, when we were at 1, the log was equal to 0. When we were at 10, it was equal to 5. And then, like I said, if you put in negative values for your, or sorry, not negative values, if you put in smaller and smaller values, so if I had put in 1/2, I would get a value. If I had put in 1/3 or 1/4, I would get values. So what happens to our graph is it gets closer and closer, but doesn't touch. I don't know why it's doing that. I checked all the connections, so hopefully it's not too annoying for you. So they would look like that. So what does that tell us? If we take a look at these, for these functions, I'm going to try this one. Nope. Okay. Our A value was 1, our B value was a 10, these are all base 10s. A value for the second one was a 2, B was a base 10, A value for the third was a 5, and your B was a base 10. Number of x-intercepts, they all had 1. It only crosses that x-axis one time. Y-intercepts, none. It never crossed the y. It got close to it, but never actually crossed it and touched it. In behaviors, all of these graphs are increasing if you read them from left to right. So the closer they are to 0, the lower down their y value is, and the more you move your x's increase, then your y's are also increasing. So they are all increasing from quadrant 4 to quadrant 1. Our domain, so what we found out is we could use any value for x as long as it was greater than 0. Not equal to, because when you put 0 in there, it gave you an error. Your range, you could use any value you wanted for range. Because it continued, going straight up and straight down. Okay, the next question says, use a graphing calculator to graph the log function y, or fx is equal to log base 10 of x on the same axis graph y is equal to 10x, and see how these graphs are related. So let's go into y equals. I'm going to clear my second one, clear the third one, and in the second one I'm going to put y is equal to 10 to the power of x. And if I graph it, so there's y is equal to, or that's the log, and then this is the, what's the word I'm looking for? That's the exponential. So again, remember this graph would go all the way down. So if this graph continued, the blue graph continued all the way down, and the red one is going in the other direction, they are exactly opposite of each other. So our graph is going like this. This is our exponential graph, and the blue one is the log graph. So they are reflections of each other. They're the inverse. So the graphs are reflections of each other, and they reflect about the line y is equal to x. So if I were to draw y is equal to x like that, these would be the exact reflection of each other. So this point here, which we'll say, let's say this point here is at 0 and 1. On this graph here, the exact reflection would mean it's at 1, 0. Okay, so what happens now if we throw in some negative values? So if we change y, sorry, our a value into negative, what does that do to our graph? So I'm going to insert, in the first one it's just a -1, so I'm just going to put the negative in front. Oh, yes, I didn't hit insert, I hit delete. So I'm doing negative math, 1, 2, log base 10 of x. So I'm going to do -2 log base 10 of x, and I'm going to do -5. Remember to use negative and not minus, of base 10 of x, and I'm going to graph those. So that's what they look like. If I go to my table, so my negative values still have all the errors. Wait till this to move down. Okay, -1, 0, 0, 1 still gives me 0. 2, I have -301, -602, -1.505. So if I look at how that compared to when a was a positive value, it's these are just flipped. So it's that reflection in the x-axis. A affects the reflection in the x-axis. So I'm just going to write all these values in here. So this one was undefined or error, whichever, they both mean the same thing. 0, this was -.301, -.477, -.602, -.699, -.778, -.845, and -1. Okay, so for the -2, when my a was equal to -2, this was undefined. We had 0, decimal -0.6, decimal -0.95, 1.2, negative 1.4, 1.6, negative 1.7, and negative 2. When a was equal to negative 5, negatives and 0 were undefined, 1 was still 0, and these ones just were the negative 5 times the value of log base 10. And negative 5. So then it says to sketch these graphs. So when we looked at them, the x-intercepts didn't change. That was still 1 and 0, but when we got to 10, instead of it being positive 1, it was a negative 1 on the y. So same thing for our second graph. The 1 stayed the same, but the 10 went down to negative 2. And then for the third graph, the 1 stayed the same, but the 10 went down to y is negative 5. And again, the graph is going to have that curve going. So in this case, all of our graphs, if we read them left to right, are decreasing in value. My y values are getting smaller as my x values are getting larger. So to complete this table, my a value is equal to negative 1, and it's a base of 10. This a value is negative 2 with a base of 10, negative 5 with a base of 10. Number of x-intercepts, it's still the same, they're all 1. Y-intercepts never crossed. In behavior, they were all going from quadrant 1 to quadrant 4, and they were all decreasing. Remember, the decrease or increasing or decreasing is based on your y value. Domain, same thing, it's a set of values for x such that x is greater than 0. X is an element of real numbers. Our range, we can use any y value that we would like. Okay, so that's for log. Now, what about natural log? So on your calculators then, we want to use the natural log. I'm just going to pause for a second and see if I can stop the flashing again. Okay, it's not making a difference. One thing I should point out too, I went into my math. It would have been faster, I just didn't see my log button when I was doing it. There is a log button right here underneath the x squared that you could press on the left side. So these ones, we're doing natural log. So the first one says to find the values for natural log of x. So you just do ln and x. The second one was for 2 times natural log of x. And then the third was for 5 times natural log of x. So we're going to hit graph on these, but we're going to look at the table. We're more concerned about the table. Ooh, oh, excuse me. Okay, so if we go to our table, let's move down here. So, we still have errors for negative values, and when we're at 1, it still is 0. When we look at values from 2 to 10, we no longer get at 10 because we're not dealing with log base 10, we're dealing with the natural log. Okay. So we're not going to have exactly the same values. But what we can see here is when we went from being a value of 1 to an a value of 2 to an a value of 5, it was just the same thing. Multiply the value that you got in the first one by 2 or 5 to get what your coordinates will be for the other values. So let's just fill those in. So this was still undefined, undefined, so we just doubled them in the second table. So in the third table, when it's 5 times, it's just going to be 5 times whatever was in the first one. So we have undefined, undefined, 0, 3 decimal 5, 5 decimal 5, 6 decimal 9, 8 decimal 0, 9 decimal 0, 9 decimal 7, 11 decimal 5. So if we want to sketch these graphs, the graphs are going to look a little bit different, except for that x-intercept. That x-intercept still occurred at 1 and 0, but then the graph, next closest one, I think, was at 7. It was at 1.9, so it was close to 2, but not quite. So we can put it, so that, I mean, show that it's kind of there, but not really. And then again, it would continue down from there. So for, whoops, so this was natural log of x. For 2 times natural log of x, again, this stayed the same at 1, 0. And then if you take a look at the chart, the next one that was kind of close to, if we, well, let's stick, well, I guess it doesn't matter. You can pick whichever one. If I stick with 7, it was at 3.8, so it was almost at 4, but not quite. So again, that's what my graph is going to do. And then for 5 times the natural log of x, again, it was at 1, 0. And then the next one, well, at 2 is at 3.5, or almost 3.5, so 2 is 3.5. And I can't do the rest because it's, so it would look like that. Okay, so if we fill in the table, sorry, I had to cough there. Okay, so now if we fill in our table, our A for the first one was 1. Our B, natural log of x, means that our base was an E. This second one, A is a 2, our base is E, base is a 5. Sorry, A is a 5, base is an E. Number of x-intercept, no y-intercepts. And again, just E is equal to a value of 2.718, and it continues on. There's a little bit more information for it in the textbook. I don't go into great detail with it, but you'll get the idea. So our end behaviors for all of these, it is increasing from quadrant 4 into quadrant 1, and I guess that's all. It's increasing. Okay. So we have increasing quadrant 4 to quadrant 1. Domain hasn't changed. Still greater than 0 and an element of real numbers. And our range, we can use any real number that we choose. So on the graphing calculator, if you do a comparison of y is equal to natural log of x and y is equal to e of x, you're going to find something similar to what we saw in the other one. So remember, to go from this, the log, to the exponent, it's always our base to the power of what the answer was equals what we were trying to get. So those are just opposites. And they get confusing because they switch the x's and y's where they want them to be. But basically this is saying what to the power of e to the power of what is going to give you your x answer. So if we do this on the calculator, I'll leave that one, but I'm going to clear that one and that one. Your e value is just the second function of log, so e to the power of x. So if I graph these, there's y is equal to natural log of x, and here is y is equal to e to the power of x. So again, they're exactly the opposite. So here's our exponential graph, and sorry, yeah, that's the exponential. This is the log. So again, they're going to be reflections or symmetrical about the line y is equal to x. So then the last part here is on the negative values. What's going to happen when you put in negative values? So I'm just going to do, I'll just go straight to our graph here. So I'm going to insert negative there. This one I'm going to clear and do, this is a negative 2 log of x, and then negative 5 natural log of x. So as you probably figured out, it's going to give you the exact opposite. It's going to be flipping it about that x-axis. So then if you go to your table, all of your y values have now turned from positive to negative. So we can just fill those in on our charts. I'm just going to hit pause and fill it in so it doesn't take as long to record this. Okay, so those are the values. All it did was took the ones we did in the last part and put negative for the y values. So if we go to draw these then, what we found from looking at the picture is that they went down instead of up. So they were decreasing instead of increasing. So for our values here, excuse me, it was still 1 and 0, but negative, so 7, it went down to negative 1.9. For the negative 2, a equals negative 2. Again, it did the same thing. It went at 1 and 0, but at 7, I think 7 is the one we used last time. At 7, it was negative 3.8, so almost at 4. And then at 5, again, we had 1, 0. And then I guess we'll go with 2, which was at negative 3.5. our graph would continue like so. So what did we figure out from this? Our A is equal to -1 in the first one, and our base was that E, or -2.7178, whatever it is. A was a -2, our base is E. A is -5, base is E. Number of x-intercepts, 1, 1, and 1. Never crosses that y-axis. Our n behavior, well, if we read from left to right, our y values are decreasing. And they decrease as they go from quadrant 1 to quadrant 4. Domain, again, nothing's changed. If x is greater than 0, or we can use any value greater than 0, and we can use any y we want. Okay, so now the last part here is just matching some of the graphs to an equation based on what we know. So if we look at the graphs, our first graph here is based on the shape of it. We know that we're looking at a positive. Our y-intercept in this one happened at 2. Let's take a look at this one. So it crossed at 2. So we know, because it's got a y-intercept there, that it can't be a log function, because log functions didn't have y-intercepts. Exponential functions can have intercepts. So we know that this is an exponential because it's got a y-intercept. So y-intercept is at 2, so that means that's equal to my a value. Now this graph, because it's when we start going from left to right, our y values are becoming less and less and less. So this is an decreasing graph. So that means for it to be decreasing, our b value has to be between 0 and 1. So if I take a look at my 4 choices here, I've got 2 that are exponential, b and d. However, d has an a value of 5 and a b value greater than 1. So I know my choice for this one then is B. So, second graph. I know that it's logarithmic because it's doing quadrant 1 to quadrant 4 to quadrant 1. Okay, so it's an increasing, and because it's using quadrant 4 to quadrant 1. Exponentials will use quadrant 2 and quadrant 1. So I'm going from quadrant 4, increasing from quadrant 4 to quadrant 1. So that means I know it's logarithmic. I've got my x-intercept, also no y-intercept. That also tells me it's logarithmic. So because this is increasing, I know my a has to be greater than 0. To be decreasing, my a would have to be that negative value less than 0. So if I take a look, my log ones, I've got natural log and log, both log functions. C has a positive a value, so I know that this one here has to be C. Okay, the second one, again, it's going from quadrant 1 and quadrant 4. This is a decreasing, quadrant 1 to quadrant 4. There is no y-intercept. So So those are two reasons why I know this is a log function. This one is decreasing. When I go from quadrant 1 to quadrant 4, it's decreasing, so that means that A has to be less than 0. So between my choices there and what I'm left with, I know that this has to be choice A, because it has the negative A value. And then the last one, of course, since it's the last one left, but if I look at this, I know I have an exponential because I'm going from quadrant 2 to quadrant 1. My graph is increasing, so that means that my B value is greater than 1. My y-intercept was equal to 5, so that means A is equal to 5. So 5 base of 2, which is greater than 1, so this is choice D. So when you're doing these, take a look at your quadrants first of all to see which quadrants they're in. 1 and 4 means that you're looking at a log. 1 and 2 means that you're looking at an exponent. And then you look at the increasing, decreasing, and the intercepts. So summary, and you can also look in your textbook on page 481 because it summarizes this fairly nicely for you into a little table there. So based on our observations, which characteristics of the graphs of log functions are similar to characteristics of exponential functions that we have studied? So the shapes are similar, they're just reflections, right? Okay, we also noticed that the graphs are just opposites or inverse. Based on our observations, which characteristics of the graphs of log functions are different than the characteristics of exponential functions? So if we do a little table here, log functions, there were no y-intercept. Exponential function, we had 1 y-intercept. Log functions had 1 x-intercept. Exponential functions have no x. Whoops. Excuse me. No x-intercept. Log functions went from quadrant 1 to quadrant 4, or they went quadrant 4 to quadrant 1, whereas exponential functions went quadrant 2 to quadrant 1, or quadrant 1 to quadrant 2. In log functions, our domain was restricted. In exponential functions, you can put whatever x value you want, right? You could have x to a negative value, you could have it to a fraction, doesn't matter. You can use any of them. For a log function, I could use any y value that I wanted, so your range. But for my y in exponential functions, excuse me, I was restricted. My range is restricted. I'm not going to get a negative value from an exponent. So if I have 2 to the power of negative 7, that is not going to give me a negative y value, it's going to give me a fraction. Okay, number 3. Can you predict the end behavior with functions y is equal to a log bx or y is equal to a times natural log x based on the parameter of a? So, yes, you can. If we looked at these, if our a was greater than 0, our functions were always increasing. If our a was a negative, then our function was decreasing. So if a is greater than 0, our function increased from quadrant 4 to quadrant 1. If a was less than 0 or negative, the function is decreasing from quadrant 1 to quadrant 4. And the last part says, in log functions of the form y is equal to a times log base of b of x, did changing the base from b equals 10 to b is equal e cause any of the characteristics to change? And it didn't. Whether you have a natural log or a base of e or you have a base of 10, it still followed the same thing. It was errors or unidentified for negative values of x, and it's still, if a was positive, you still had increasing values. If a was negative, then you had decreasing values. So if you look at those charts, all the characteristics stayed the same. You still had no y-intercept, and you had one x-intercept. Your restrictions on the domain and range didn't change or anything like that. So that was a long one, lots of information in there, but hopefully it'll help you get through those textbook questions.